So, which laptop are you going to use? Is he going to use that laptop? Yes. Are they converted now? Lord.
I left my...
Well, last year when I was in standard 6, the school introduced a club called the Media Club. I decided to join it, then I got accepted. And that's how we came to make the future of this land. Like my grand queen mother would say,
be fearless. Be like your father.
Well, in the film, I learned a lot about acting and types of shots that the camera takes. And my favorite character in the movie is Maxine, the place where my father was born. A place his forefathers lived and passed on to the afterlife. Now it's just a place. I was surprised to see myself in the newspaper.
This is the first time. How did your parents feel about that?
My parents felt proud and happy for me.
I'm a teacher at our academy. Currently I'm teaching physical education.
Place of my giant ancestors.
Watching myself on the big screen, wow, that was mind-blowing. I would watch some movies on the big screen, but now to see myself there, it's like looking at yourself in the mirror and wondering who else is watching you. That is amazing. My favorite part was when I had to cup in with the magic stick and it sounded like an earthquake, like a lightning bolt.
He brought peace amongst our people and all tribes.
And then my first lines, imagine a war caused by peace. That was nice.
Imagine a war caused by peace.
But you always said peace was the end of war, not the cause of another.
A hunt to kill.
Alright, so we run for 45 minutes. We have these COVID protocols. So we start today. My name is, I'm going to take my mask off so that you guys hear me. Then we emphasize on these. And then we continue with the lesson for 15 minutes. For a break, I'll show you the board there. It's time for a break. Then we say we're going to go for a quick break. We'll be right back. Then I'll brief you up during the I think I got the role because of my martial arts. I knew karate, went to karate school, and I tried to fit in so that I can do more exercises and be able to get that. In Botswana here, I know that we have a low population. So what I want is that the children to be inspired and it should go to other countries to show that the children, no matter how young they are, they can do well in their lives.
People worth saving.
They're not the kind of people worth saving.
Like in Botswana, we watch India's TV, we always see Studio Universal movies. I want our movies to also be shown on Studio Universal and be proud of ourselves as Botswana.
A hunt to kill.
Yeah!
Good day, viewers. Welcome to another session of the Teleradio Ask Your Teacher. My name is Mr. Ganye. I'm here to present the IGCSE 0625 Physics, Atomic Physics, stroke Radioactivity, Section 5 in the Physics syllabus. We need to remember the COVID-19 protocols. Stay safe. Wash your hands with running water. Always mask up. Sanitize. Maintain your distance, social distance. For the sake of this broadcast, so that you can hear me clearly, I'm going to remove my mask, but always maintain your COVID protocols. Moving on, we are looking at atomic physics, section 5 in the IGCSE physics. We move on. A general review of the topic. We are going to look at atomic structure. We are going to look at radioactive decay or radioactivity. We are also going to look at the characteristics of the radioactive emissions which are emitted when an atom decays. That is alpha, beta, and gamma. We are going to look at detection of these radioactive emissions. How do you detect them? We are going to look at calculations involving half-life. We are also going to look at safety precautions when you are handling them or you are using them in the lab. Then in between the lesson or at the end, we'll be having examination questions which are based on this topic, which you need to attempt as you move along. We might not be able to cover all the sections, but we'll cover atomic structure, radioactive decay or radioactivity. We'll also cover characteristics of radioactive emissions. We move on to slide 3. When we look at radioactivity or atomic physics in general, we are looking at a special group of elements or atoms which have the ability to break down and release some emissions. They are a special group of elements. That's why we need to talk about them. Our topic starts by looking at the general atomic structure. This is part of your chemistry. We are looking at the atomic structure there, and we are saying atoms are made up of a nucleus in the middle, which is a central heavy body. They are also made up of electrons. The nucleus is composed of protons and neutrons. The electrons are found orbiting around the nucleus in shells or orbits or orbitals, and at a high level we'll be calling them energy levels, as shown on the slide there, slide number 3. We move on. We are still on atomic structure. We have a summary there of the subatomic particles which you find inside the atom. You need to know the name of the particle, the relative charge, the relative mass. As shown there, look at the proton. Protons have a charge of positive 1. They have a charge of 1 atomic mass unit, followed by neutrons, which are also having a relative mass of 1, and they do not have a charge. They are neutral, 0. We have the electron with a charge of negative 1 and a relative mass which is very small there, 1 over 1890 or 1 over 2000, which can be considered negligible, but it's there. We move on to some terms that we need to know, definition of terms, like the term nucleon. The term nucleon is used to refer to particles in the nucleus. All the particles in the nucleus, we call them nucleons. So that is, protons and neutrons are called nucleons. We have the term nuclide. This is used to refer to a nucleus with a specific combination of atoms and neutrons. We move on to slide 5. We are now representing the information which we find on an element. We are representing it using what we call the Nuclei Denotation, as shown there. If you look at the Nuclei Denotation, we are just taking this from your periodic table in chemistry. There are two important numbers which we have to talk about there. There's a number indicated on top of the element shown as A, which is the nucleon number. And in chemistry again, we call it the mass number. By definition, what is the nucleon number represented by A? This is the total number of nucleons. That is the total number of protons and neutrons in an atom. And we said it's also called the mass number. We've got the proton number shown by the letter Z. This is the number of protons in the nucleus of an atom. So when you define that one, make sure you give the full definition. The number of protons in the nucleus of an atom. And in chemistry, we also call it the atomic number, shown by the letter Z. And if you are looking at your periodic table, it's the smaller number on the element there. It can be written on top, it can be written below, depending on the periodic table that you are using. But for the purpose of this lesson, we are recording it at the bottom there as the proton number or atomic number. We move on to slide number 6. When we look at chemical elements, some of them have got what we call isotopes. So we are looking at isotopes. By definition, what are isotopes? Isotopes are atoms of the same element that have the same number of protons and different numbers of neutrons. For example, we have got carbon 12 and carbon 14. Carbon 12 there is showing that it is coming with the nucleon number 12, and carbon 14, nucleon number 14. But if you look at them, they are all elements of carbon, atoms of the element carbon. And they've got a proton or atomic number of 6, all of them. But they differ now on the mass number or the nucleon number, which means they also differ on the number of neutrons. Their chemistry is the same. If you want to look at their chemistry, because the chemistry of an element is determined by the electrons, especially the electrons in the outermost shell, the valence shell. So they are also going to be having the same chemical properties. That is carbon 12 and carbon 14. We have also another example there on slide 6. Hydrogen. There are 3 isotopes of hydrogen which have been identified there, which you can call hydrogen 1, hydrogen 2, hydrogen 3. Let's look at hydrogen 1, the first one. It has got a nucleon number 1, proton number 1. And we are saying it has got only 1 proton. Same thing with hydrogen 2, 1 proton. And the same with the hydrogen 3 tritium with proton number 1 or 1 proton. How do we get the number of neutrons which are indicated there? 0, 1, 2. You subtract the mass number or the nucleon number, subtract the proton number or the atomic number. So for hydrogen 1, we are saying 1 minus 1, we get 0. So hydrogen 1 does not have neutrons. Hydrogen 2, we are saying 2 minus 1, and we get 1 neutron. Moving on again, you can do the same for the hydrogen 3. We move on to slide number 7. We are still on isotopes. There are 2 types of isotopes which we have. We have got non-radioactive isotopes, and we have got radioactive isotopes or radioisotopes. For the purpose of this lesson, we are very interested in the radioisotopes, the radioactive isotopes. Remember our topic, radioactivity. What are these radioisotopes? Radioisotopes have an unstable nuclei which can break down and emitting or giving out these radioactive emissions which we are interested in under this topic. So radioisotopes or radioactive isotopes have unstable nucleus which can break down or disintegrate and in the process release some radioactive emissions, which are alpha, beta, or gamma. Some uses or applications of radioactive isotopes, we are summarizing them here. It will be in another session or another lesson where we go in detail on these ones. These chemical elements, radioisotopes, they're very important uses in our everyday lives. Like we are seeing, they are used in the medical field to treat cancer, a process called radiotherapy. We are going to use gamma rays to direct them at a cancerous cell and in the process sort of burn it out. So that is radiotherapy. They are also used for sterilization of medical equipment. When you clean the medical equipments which are used there in the hospitals, they use gamma rays. They are able to kill the bacteria and to kill the microbes. We've got industrial uses, point number 2 there, where we are using them now outside the medical field. What do we use them for? We use them as tracers, where we are tracking or tracing leakages in underground pipes, which can be carrying oil or gas. Even we use them for monitoring the thickness of paper. We use them for alpha radiation use in smoke alarms. So we'll go into details later on this one. Here is just a summary of these ones. We now have our radioactive elements. Where does radioactivity come in? Where does radioactive decay come in? We are moving on to the next slide, slide 8, where we are now introducing radioactive decay, where we are seeing that we have these chemical elements, we have these atoms which are special, and they are undergoing disintegration now. They are undergoing breakdown. Radioactive decay, the process by which a radioactive unstable nucleus disintegrates or is altered to make it more stable. It can do that by releasing some emissions which we are interested in our topic. So we have got a parent nucleus which will undergo decay or disintegration to form a daughter nucleus, and these particles now, or the radioactive emissions. Point number 3, radioactive decay is the spontaneous transformation of an unstable nucleus into a more stable one by release of radiation. This is a random process, which means one cannot know which nucleus would decay. That's why it's called the random disintegration or the spontaneous disintegration of the atom. We also call it radioactivity. We move on to slide number 9. When radioactivity takes place, or when radioactive decay takes place, we have said we release 3 main types of emissions which are interested in at our level. We are interested in the alpha particles or alpha decay, beta, and the gamma decay. So those are the 3 main types of emissions which we need to focus on. There are others. We look at them at a later stage up the ladder. Slide number 10. We start with the alpha emission or alpha decay. What happens when the nucleus of a radioactive isotope decays by alpha emission or alpha decay? We are saying a part of the nucleus is going to break off. A part of the nucleus is going to break off, and it goes away with 2 protons and 2 neutrons. So an alpha particle consists of 2 protons and 2 neutrons. These are coming from that large unstable nucleus which we had. So if a chemical element undergoes alpha decay, we are saying the proton number or the atomic number is going to decrease by 2, because there are 2 protons which are going away. The nucleon number or the mass number is going to decrease by 4. Remember, the nucleon number is a combination of neutrons and protons. So is going to decrease by 4. We move on to slide number 11. What are the characteristic properties of an alpha particle in terms of its nature, its charge, its ionization level or power, its penetration power, and its behavior in a magnetic or electric field, that is deflection? Let's go through those ones. The nature. An alpha particle is a helium nucleus. And I emphasize, an alpha particle is a helium nucleus. A very common question in multiple choice, where they now put helium atom as one of the options. And if you are not very careful, you will pick helium atom. But we are saying it's a helium nucleus because it only contains particles which are found in the nucleus. That is 2 protons and 2 neutrons. It does not have electrons, so we can't classify it as an atom. Take note of that one. An alpha particle will be carrying a charge of positive 2, which is coming from the 2 protons that it is carrying. Ionization, the ability of this alpha particle to knock off electrons and create charges in other atoms. That's ionization. We are seeing that an alpha particle has got the highest ionization power there. It can knock off electrons and form ions in the atoms which comes across. Penetration power, alpha particles have the weakest penetration power. So they can be easily stopped by a sheet of paper. They cannot pass through a sheet of paper. And we say they've got a short range. They lose most of the energy in the ionization process, so they don't travel that much. Deflection. How do they behave if they are to pass through a magnetic field or an electric field? We are seeing that alpha particles, because they are charged, they are carrying a positive charge, they are going to deflect. And they deflect in opposite to the other next particles which are going to talk about, the beta particles. Alpha particles, if it is in an electric field, because they are positive, they deflect to the negative side. Right, we move on to look at slide number 12. Alpha decay nuclide equations. Alpha decay nuclide equations. We want to summarize what we have said up there. What happens when an atom undergoes alpha decay? And we are saying, how do we represent that? We use what are called nuclei decay equations as shown there. X representing our element, A representing our nucleon number, and Z representing our proton number. And we are saying, when alpha decay takes place, the mass number or the nucleon number is going to reduce by 4. So we say subtract 4. The atomic number is going to decrease by 2. So we are saying subtract 2. And we form the alpha particle or alpha symbol shown there, 4, 2. There's an example or 2 examples given on that slide where we are using radium-226 undergoing alpha decay. So from 226 we are saying subtract 4. We get 222, and this is radon-222, and we have our alpha coming outside again. There is polonium-212, the second example shown there. We are subtracting 4, and we get 208. Then again on the proton or atomic number, we are subtracting 2, and we get 82, plus our alpha particle. We move on to slide number 13. When you come up with your nuclide equations, they have to be balanced also, like what we do with the ordinary chemical equations in chemistry. So make sure they balance in terms of the number of particles, in terms of charges. The sum of the upper numbers, the mass numbers on the left of each equation should equal the sum on the right. So they have to balance the numbers. Then the sum of the lower numbers, the atomic numbers, should also balance. So take note of that one when you balance your equations. Slide 14, we have got a beta decay. We are introducing beta. A beta particle is a high energy electron which is emitted from the nucleus. A high energy electron which is emitted from the nucleus. It starts as a neutron which is in the nucleus, and that neutron undergoes some changes and it forms a proton and an electron. Then the electron will shoot out of the nucleus, out of the atom, and exist outside. And we call that our beta particle. So beta particles are electrons which are coming from the nucleus. Don't confuse them with other electrons which are on the shells or in the orbits there. These ones is coming from the nucleus. That is what makes these chemical elements special. Let's look at beta particle decay. When a chemical element undergoes beta particle decay, we are seeing that the proton number is going to increase by 1 because we are giving birth from a proton coming from the neutron. So the proton number, the number of protons increases by 1, and the nucleon number does not change. It remains the same. So that is the beta. We move on to slide number 15, where we've got a summary of beta decay equations. Look at the beta decay equation. The top number, the mass number, the nucleon number does not change. It remains A. But the proton number changes. It increases by 1. Look at the example given there for carbon 14 undergoing decay. And we get a nucleus of a nitrogen which is 14,7. The proton number is increased from 6 to 7 because we've given birth to a proton. And alongside that is our beta particle. Look at the symbol for a beta particle, 0, -1, and the beta sign. There's also another example there of iodine 131, which is now forming a nucleus of xenon 131. The atomic number is increased from 53 to 54. We also produce other particles there like the antineutrino, and we are not interested in that one. We are only interested in the beta. Let's move on to slide 16. Summary of the beta particles, their characteristics in terms of nature, charge, ionization, penetration. Beta particles, I've already said, these are high energy, fast moving electrons. In short, beta particle is an electron. And since they are electrons, they carry a charge of -1. Ionization, they have moderate ionization power. They have medium ionization power. Less than form of alpha, but more than gamma. Penetration, they've got weak or moderate penetrating power. They can pass through paper, but they can be stopped with sheets of aluminium, as you see on the other slides coming. Deflection in a magnetic field and electric field, because they are charged, they deflect. And they deflect in the opposite direction to the alpha. We move on to slide number 17, where we are looking at gamma decay. Remember, after a decay either using alpha or beta, the energy levels of the chemical element do not remain the same. They change, and that difference in the energy levels is what is going out as a gamma emissions or gamma electromagnetic radiation, which is basically energy there. So gamma particles is a form of electromagnetic radiation or energy, which we are now getting after alpha or beta decay. So being energy, it does not have charge, it does not have a mass. We can only see its effect, like if burning can take place because of the presence of that high energy, which is gamma. It has got very strong penetrating powers. Gamma particles can penetrate virtually anything in front of them. They can be stopped by a thick lead plates. You need to use lead plates. They are least ionizing, but because they have the ability of entering our bodies, they can now ionize our body cells, causing cell mutations, causing all those cancers which we can talk about, because they can penetrate the cells. If they cannot penetrate, then it's better. Right, slide number 18. We've got what is happening in alpha and beta. On the left there, we have got a nucleus, and we are seeing a part of the nucleus breaking away, indicated there as radiation. We are saying that is an alpha particle which is disintegrated from the nucleus. So that one on the left is showing alpha decay. On the right, we've got beta decay. Beta decay, we are seeing a neutron which is in the nucleus undergoing some changes, and it gives birth to a proton and an electron. And the proton in blue there shoots out of the nucleus, out of the atom, and exists as an independent entity outside, and we are saying that's an electron. The proton will remain inside, and our proton number is now increasing, like what we have seen there by 1. We move on to slide 19, showing the penetration power. We're talking about these ones. Look at the diagram there. We've got alpha particles which are being stopped by paper. Alpha particles have the weakest penetrating power. They cannot pass through paper as shown there. Beta particles, moderate penetrating power. They can pass through paper but can be stopped by few millimeters of aluminium as shown there. Look at gamma rays or gamma emissions with the strongest penetrating power. They can pass through paper, they can pass through aluminium, and they can now be stopped by lead. And you need to use thick lead plates. If you use very thin lead, they can penetrate it. They've got very strong penetration power. We look at deflection. Next slide, 20. Deflection of emissions. How do they behave in an electric field? We've got a negative plate, a positive plate, and we are passing the emissions through. What happens? If we look at gamma, because gamma is uncharged, it can pass through, represented in blue there, passing through the electric field without deviating, without changing direction or turning. Look at alpha and beta. Alpha particles, because they carry a positive charge, they are deflecting in an electric field. As shown there, they are deflecting to the negative plate because they are positive. Then beta particles are deflecting to the positive plate because they are negative. Opposites attract. We are interested in the degree of deflection shown there. If you can follow the red line for alpha and the green one for beta, you see that alpha particles have a weaker deflection than beta particles. Beta particles are strongly deflected, and we need to explain why. It has to do with their mass. It has to do with inertia, another concept that we look at in physics. Alpha particles are heavier, so we talk of high inertia, resistance to change their velocity, to change their position. Beta particles are very light. They can easily change their position. Moving on to slide 21, where we have picked some questions, common questions that we get across the core and the extended options of our IGCSE physics. These are summarized questions which we have picked common on this topic. We look at question A or 1. A nucleus of nitrogen 13, Nuclei Denotation is shown there as 13.7, and we are required to determine the following: the number of protons in the nucleus, the number of neutrons in the nucleus, the number of electrons in the nucleus. Number of protons is already shown, is the proton number, which is 7, the smaller number shown there. So A1, the answer is given there, is 7 protons. Number of neutrons. We said for us to get the number of neutrons, we have to subtract those two numbers. Because the mass number or the neutron number is a combination of protons and neutrons. So we need to subtract 13 subtract 7, which gives us 6 neutrons as the number of neutrons there. Then part 3, the number of electrons in a neutral atom. In a neutral atom, where we say atoms are electrically neutral, because the number of positives equals number of negatives, meaning the number of protons equals the number of electrons. So, since we have 7 protons, we are saying we are also going to have 7 electrons. So, this is a typical question which is coming, especially in core option. You get that kind of a question, and if you are doing chemistry again, you also do the same thing there on the atomic structure. Second question there are 3 naturally occurring isotopes of hydrogen. There is hydrogen 1, hydrogen 2, and hydrogen 3. The nuclei denotation of hydrogen 1 has been shown there, 1 1 is shown there. Then you are required to write down the nuclei denotation symbol for hydrogen 2 and hydrogen 3. That is the question which is coming there. To write the nuclei notation for hydrogen 2 and hydrogen 3. When you say hydrogen 1, hydrogen 2, hydrogen 3, we are already indicating the nucleon number. We are already indicating the mass number, the bigger number which you are going to put on top of the element. So hydrogen 2, it means on top we have 2, then at the bottom we have 1. Remember hydrogen with proton number 1, and these are isotopes. They all have the same number of protons, which is 1 1 1. So for hydrogen 2 is shown there 2 1. Then we have got hydrogen 3, and we have already said by saying hydrogen 3 we are already commenting on the mass number. We are already indicating the nucleon number, which is 3. So hydrogen 3 is shown there as 3 1. The proton number is the same. If you can look at them, they all have the same proton number 1. Hydrogen 1, hydrogen 2, and hydrogen 3. They all have the same proton number 1. So you should be able to represent these symbols using nuclear notations as shown on those 2 questions. Hydrogen 1 and hydrogen 2, hydrogen 3. Thank you very much. We are going for a short break. When we come, we'll be tackling questions and answers. Remember your COVID protocols. Stay safe. Wash your hands. Mask up. Sanitize and maintain your distance. Thank you.
There are people out there, people worth saving.
They're not the kind of people worth saving. A hunt to kill.
Bernard Per Queen's Club on Tuesday. And those were our sports update. Thank you very much.
All right. Do you know what FIFA stands for?
Wow. I don't. I'm so disappointed.
Even the bell is disappointed.
Okay.
to your future.
You can't live without. This is your radio. Only the best internet.
I am an in-school participant at Stepping Stones.
Great.
I was doing a scholarship program.
Okay.
And yeah, I'm actually doing my Form 3.
Where?
At E2 CJSS.
Wow, you should have come to the TDA. The Dow Academy is go radio, it's go building computer, and it's go mechanics program. We do coding, man. We do like the Walt Disney stuff, like we draw anime, graphic novels. You know about that?
Yeah, it's kind of like the Harvard of Machu.
It's the Harvard of Machu, God! I'm telling you, oh, man.
Welcome to your future.
You can't live without. This is your radio. Only the best internet radio station in the world.
Welcome back. We continue. Remember to mask up, stay safe, sanitize, and maintain your distance. Our topic today was atomic physics, radioactivity, or radioactive decay, where we're interested in looking at some chemical elements which undergo decay, radioactive decay. We are in the question and answer session. We have got some questions which we are looking at from the IGCSE past exam questions. Slide 22, there's a question on carbon 12 and carbon 14, which we have said these are isotopes. Look at that, they have the same proton number, 6, and they differ on the mass number or the nuclear number. The other one is carbon 12, the other one is 14. So that makes them isotopes. Part A of the question, you are required to complete that table. Number of electrons, number of protons, number of neutrons. So you look at that. Number of protons, if I can look at that one, is the same. The proton number shown there, 6. And it's the same on the other side, 6. Right, let's go to the next question, which is talking about technetium 99. Is a source of gamma rays used as a radioactive tracer. It is produced from molybdenum 99, which emits beta particles. The symbol of technetium is shown as Tc, and the symbol of molybdenum is shown as Mo. You are required to complete the nuclear equation for this decay. This is the decay of molybdenum undergoing beta decay, 9942. You will not need to use a periodic table. In the physics exam, you will not be given a periodic table. It's just you handling or manipulating those numbers that are given there. Let's look at this question now. It's answered on the right side there. Remember, it's undergoing beta decay, where we said a neutron in the nucleus undergoes some changes, and in so doing, it produces a proton and an electron, which is the beta particle which shoots outside. The proton does not go anywhere, it remains inside. So we are seeing the proton number increasing now from 42 going to 43, because we gave birth to a proton, as shown there. This does not change the mass number or the nuclear number, 99. So with technetium being formed there and the beta particle going out. We move on to the next question, where they are saying state another use of radioactive nuclides in medicine. Another use, which means if you go to the stem of the question there, they'd given us the other use. If you are following there, it's indicated that it is used as a radioactive tracer, either in the human body or, as we have said, tracing for leaks, blood flow, and all those things. So they are now requiring you to come up with another function. It means you're not going to repeat radioactive tracers because it's already been given. So you think of other uses, and in this case, those which are in the medical field, you're not going to generalize and just talk of any other use. You're going to mention in medicine as the question requires. So we have indicated two uses there. Sterilization, where we're saying this is the cleaning of the medical equipment that is used. You're talking of those syringes, you're talking of all those other items which they use in the medical field. They are cleaned by gamma radiation. Another use is radiotherapy, treating of cancerous cells in the body, where you direct a laser of gamma rays onto the cells and they absorb those gamma rays. Then in a way you are burning them, trying to control that they don't keep on multiplying. So that is a use in the medicine world. We move on to slide 23, where we've got two questions again. The other question, part A, you are going to do that as you do your revisions. We'll go to part B, where we are looking at a radioactive nucleus of carbon decays to a nucleus of nitrogen by emitting a particle. Complete the nuclide equation and state the name of the particle. The nuclide equation is already given there and you are just supposed to complete it. You look at what has happened there. We are moving from carbon 14.6 to nitrogen 14.7. What is interesting there is the increase in the proton number from 6 to 7. And if you are following there, you should be seeing that this takes place when there is beta emission or beta decay, which we said a neutron in the nucleus undergoes changes, gives birth to a proton and an electron. That is why our proton number is increasing from 6 to 7. So that is showing beta decay. Name of particle X, which is produced there, is supposed to indicate beta decay. So those are some of the questions that we have. And on the slides, there are other questions which you can do, which we have not answered together in this platform, but you can as well go on to answer them. Going back to a recap, a summary of our lesson for the day. We're looking at section 5 in the physics syllabus, where we are looking at atomic physics stroke radioactivity. We started by looking at the chemistry background, where we are looking at the structure of the atom. This is also the same in chemistry. Those who are doing chemistry will benefit twice, where we're being introduced to the structure of an atom, saying it's made up of protons, it's made up of neutrons, which we find in the central body, which is heavy in the middle there, the nucleus. Then we also said there are electrons which are revolving or orbiting around the nucleus in shells or in orbits. Later on, you can call them energy levels. We looked at these subatomic particles, where we were interested in their mass, in their charge, and also their relative positions, as we have said. The proton is coming with a charge of positive 1. It has a mass of 1 atomic mass unit, and we find it inside the nucleus. The neutron is coming with a mass of 1, and it does not have a charge. It's neutral, 0. From there, we introduced isotopes, atoms of the same element, having the same proton number but different neutron numbers. And we said from these isotopes, we get radioactive isotopes, which are the focus of this lesson or this topic. Radioactive isotopes or radioisotopes have unstable nucleuses or nuclei which will disintegrate or break down, releasing the 3 emissions which we are interested in this topic. They will release alpha, they will release beta and gamma radiations. We went on to look at alpha, the characteristics of alpha in terms of nature, charge, mass, ionization level, and penetrating level. And we said alpha is made up of 2 protons and 2 neutrons. Alpha is a helium nucleus, and we emphasize, don't confuse it with a helium atom. Then from there, we went on to look at beta, which we say these are fast-moving, high-energy electrons which are shooting out of the nucleus. We have also talked about what a beta would do to an atom or a nucleus, where we said there's an increase in the proton number because we have given birth to 1 proton. We also talked about the gamma, where we said before dissociation and after dissociation, the energy levels don't match. There is extra energy which needs to be released, and that is gamma. So gamma is basically electromagnetic radiation or energy. It has no charge, no mass. We talked about deflection of all these emissions in an electric field, in a magnetic field. And we were looking at nuclide equations. So that is a summary of our topic, radioactivity, atomic physics. We'll do more when we come back and look at half-life. There are calculations under half-life which we need to look at in another session, another lesson. Then we'll also look at safety precautions when handling these radioactive emissions, and also when you are disposing them after using them. Then we'll conclude the series by looking at their applications, their uses in everyday life. Thank you very much for tuning in to the session Ask Your Teacher. Remember, continue to maintain COVID-19 protocols. Stay safe all the time. Wash your hands with running water. Always put on your mask. Sanitize. Maintain your distance. Thank you. See you in the next lesson.
The music just feels so good. You're on the number 1.